Hello friends, welcome to engineering tutorial. So in today's video we are going to discuss about the second order time response of a control system. Okay, so in the previous videos we have already discussed about the first order system, its basic representation, the open loop and closed loop transfer functions, and the output response for various control inputs. So in this video we are going to discuss about the time response for a second order system. Okay, second order system. So if we try to remember the definition of order of a system, it is the highest power of S in the characteristic equation of the closed loop transfer function. Okay, so the basic layout, the basic design of a control system is in this way. So this is the forward path gain, this is the feedback path gain, all in S domain or the Laplace transform domain. This is the summing block, this is the output, feedback, negative feedback is used always, and here is the input in S domain. So this is the basic design. Now for the analysis of a second order system, the forward path is normally taken in this way. Okay, omega n square by S into S plus 2 zeta omega n. Okay, this is the forward path transfer function. Sometimes it can also be written in this form. Okay, omega n square by S into S plus 2 delta omega n. So don't confuse between these two symbols. They mean the same thing, which we'll discuss in a moment. So this is the forward path transfer function, and the feedback path, it is generally equal to 1, means unity feedback. Hs is equal to 1. Okay, so always remember these two important things, which is generally used for the analysis of a second order control system, the time response or the output response. The forward path transfer function, okay, the forward path gain in S domain, it is omega n square by S into S plus 2 zeta omega n or 2 delta omega n. Okay, so the symbols, it may vary, but they mean the same thing. Okay, now what do these symbols mean? So this omega n is called as the natural frequency of oscillation of the system. Okay, natural frequency. Okay, or it is also called as the undamped natural frequency. Okay, this delta or zeta, whatever you may find, this is called as the damping ratio of the system. It is called as the damping ratio. Okay, Omega n is the natural frequency or the undamped natural frequency of the system, and this delta or zeta, it is called as the damping ratio of the system. We'll discuss about the significance of these symbols when we go deeper into the analysis, but just for now you understand, you remember these things, okay, so that it would be easy while discussing the output response of a second order system to various inputs, control inputs. For now you just understand and remember these things. Afterwards, in separate videos, I will discuss about the significance of these things. What is damping ratio and what does it mean in its physical significance? Okay, so we'll discuss that. So this is the basic layout of a second order control system, with this being the forward path gain and this is the unity negative feedback. So we know the next important concept related to the time response analysis is the characteristic equation. Okay, characteristic equation, which is 1 plus GS HS equals to 0. Now here this is GS and this HS is equal to 1. So the characteristic equation, this becomes 1 plus omega n square by S to S plus 2 zeta omega n into 1 equals to 0. Okay, so if we further simplify it, this becomes S into S plus 2 zeta omega n plus omega n square equals to 0, or it becomes S square plus 2 zeta omega n S plus omega n square equals to 0. So this is the characteristic equation of the system, the characteristic equation. Now, so the definition of order, it says that it is the highest power of S in the characteristic equation of the closed loop transfer function. So here this is the characteristic equation and the highest power of S is 2. Okay, the highest power of S is 2. So that's why it is a second order system. The highest power of S in the characteristic equation is 2, so it is a second order system. Okay.